the relationship, the computer and game technologies. So let me start off with the computer as a game technology. A computer is a medium for delivering a game, and as such, it is like any other media. There are many media for delivering games. You can do cards and paper. You can have board games. That is a classic. There are a number of variations on that. Normally, you have a large board with some stuff printed on it. You have counters and things that you move around on the board. There are technologies for games involving little miniature soldiers that you are ships or planes that you put on a big flat surface and move around. Dungeons and Dragons uses very little in the way of hardware. It's mostly just a book and funny shaped dice and pads and so forth. So we have a lot of different media, and the computer is one medium. What is special about the computer? What are its strengths and weaknesses? That's what I want to talk about this afternoon. Let's see. The computer has a lot of very special capabilities. The first capability that people picked up on, the one that initially dominated all of our thoughts, was the capability of the computer to do real time. Do we have enough outlines?
Mission 2 at least.
Yeah.
Oh, just someone pass one out to Linda.
Send one out to Linda, get her a copy.
Excellent.
The thing everybody picked up on was the fact that you could do real-time play, and that was a big step because until a computer came along, all games were fundamentally limited by the fact that they were managed, refereed, executed by humans. And if it's going to work, gee, we've got to design the game so that even the dullest schmuck can figure out the rules. So we're going to keep the rules real simple, and we're going to deliberately design the game so there are lots of nice little gaps where we can catch up with the time. Even sports games, football, baseball, whatever, we're going to rig it up so there will be pauses every now and then so we can catch up and figure out what the hell is going on. So there was always this difficulty with the stop-and-go nature of game playing. And all of a sudden we have this technology here that can go full tilt boogie as fast as you want it to go, absolute real-time, no pauses necessary. And that dominated much of computer game design in the early years. Real-time was the very essence of computer games. This is why one reason, there were a variety of others, one reason why we launched into arcade games is the initial primary expression of computer game playing, because they are the highest expression of real-time game play. Very intense, boy, we're going to pop that stuff at you real fast, you're going to shoot back, and we're going to just real intense, very fast-paced action. So we really press the real-time component. But that is only one of many capabilities of the computer. Some of that is very well developed, but there are other capabilities of the computer as a technology that are less well developed. For example, limited information. One problem in many games, here I am going to interact with you. One of the neatest things that you can do in any game is somehow hide the information so that I know something you don't know. And you're going to have to make guesses, and we get into guessing games, and I was talking about poker at lunchtime. All of the interesting things that arise from the idea of me sitting here looking at absolutely nothing in my hand, and then I look at you, and yeah, boy, what I'm going to do to you with these cards. And it's all bluff! And all the interesting things that you get out of a situation like that. But the fundamental thing you need is limited information. And cards do that well. Cards are a technology designed for limited information. A lot of board games, though, have great difficulty because you can see this stuff. This was a classic problem with board war games. My background in games was in board war games, SPI, Avalon Hill, that type of stuff. And the fundamental problem we struggled with for years was the fact you could see where the other guy was. I mean, the worst example of it, did any of you ever play board war games, SPI stuff? Sniper. This was a great game, boy. Here, this was man-to-man combat. And you had a little counter that represented a man, and you had a platoon, or a squad, 8 men. And you had, your little men, and each of them was armed with a different weapon, and you'd run them around, and if the guy was wounded slightly, then you'd get the same, you'd replace the counter of him. There'd be a counter showing this infantryman. If he was wounded, you'd replace that counter with another counter showing the same guy, only there's a half symbol right next to him indicating that he's half strength. And then if he's hit again, he's incapacitated, and you take away that counter and put down a new one, showing him laying on the ground kind of, and then if he gets killed, you take away that counter and there's this counter showing him laying there, face down, dead. So, because the body was sometimes useful, you could rifle it for weapons, so you still had bleed on the map. So, it's a rather grotesque game. I mean, this game had one of the greatest rules in all of all game design. See, there were rules about whether you were, well, the position you were taking in combat, because a guy could be kneeling, he could be prone, crouching, or erect. And then there were also questions about if he was at a corner, whether he was exposed to enemy fire. And there were a whole series of rules regarding the question of whether you were allowed, to expose yourself. You had to move out, and then you could see and shoot, but if you stayed behind the corner, you couldn't. And so one of the rules was if you were behind a corner, then prone men, crouching men, and kneeling men could not expose themselves, but erect men could expose themselves. So that was a classic. Let's see. Why was I talking about Sniper? Oh yes, limited information. The problem though is, here you are playing this game with somebody, you could see where all of his men were. I mean, you move your man, oh, you're going to be coming around that corner in a minute. No problem, I'll aim a cannon right at that corner. You walk around that corner, boom. Wasn't very realistic, and it sure took away a lot of the fun. And one of the most enjoyable things I ever did was I played a game of Blind Sniper. You played blind, it was called Blind Sniper Anarchy, actually. The way it worked was you get a big room, a bunch of tables, one table for each player is one person. Then you get one referee, and they're all facing outward in a circle of tables. And then the referee just says, all right, everybody, let's go. And each guy has a rifle. But then the referee on the central map has placed grenades and machine guns and all sorts of nice toys scattered around the map. And then the idea is that the referee walks up to you and says, what's your move? And you say, and you don't say anything, you just sort of point, you show where your man moves. And the referee then looks at the main map and says, oh, look what you found. And he puts a grenade in your hands or something. And then the idea is he'll just put things down on the map if you're allowed to see them, if you've walked into a place where you can see them. Here's a gun or whatever, or an enemy who's walking away and doesn't see you, so you get to shoot him in the back and all sorts of fun things. Anyway, that was an absolute blast. It was immensely enjoyable, sneaking around, not knowing where the other guys are. I got in this great scene where I was on the roof of a building, see, because you can see down on people from the roof. And all of a sudden I heard someone coming up the stairs, and the guy, I threw a hand grenade down the stairs into view. And the next thing I know, this very angry person comes flying out of the stairs and jumps on me, and we're rolling around in hand-to-hand combat. And the referee keeps rolling the dice saying, nothing happens, you're still in hand-to-hand combat. And meanwhile, he was announcing to the world that everyone could hear these two people up on top of this roof. And so hand grenades started coming up on the roof, and then this cannon started shooting on the roof, and then the machine gun fire started coming in on the roof. And we're still rolling around on the roof. It was one of the great moments in all of my game playing. I really enjoyed that one game. My point in this long war story is that limited information makes for an awful lot of fun. If you don't know what's out there, your imagination really goes to work. And the computer can do a wonderful job of hiding things from you and then revealing them to you at the appropriate moment. So now you get into all this, what's around the corner? It's an excellent capability that has been little utilized in computer game design. There are games that have done it. I'm not saying it hasn't been done. It's been done by a number of games. But it has not been, people really haven't jumped all over this capability. Another one, an obvious one, computational power. Golly gee, with a computer you can actually compute. What this really permits is more complex handling of capabilities. In war games, we can calculate logistics and golly gee, how many rounds of ammo have you shot off and how many have been sent up to the front, and the trains can only carry 20 tons of ammo per day, and how many beans do you have to feed the soldiers, and all of those things. But you can also do economics games where we calculate prices and costs and margins and supplies and all of that stuff. There are a lot of types of games that could involve lots and lots of computation, but we've never been able to do them in the past because people had to do the computations. This is another area that we've seen a lot of work in. Obviously, a flight simulator is an excellent example, and there have been a lot of things that have done this. But again, I don't think this has really been exploited to its fullest. Telecommunications, another very important capability. The idea we can link players up in a network and all of a sudden have groups of people playing together. Fantastic capability, grossly underutilized, primarily because of the dearth of modems out there. We still don't have real penetration into the marketplace of modems, but this is an area that is steadily growing. Modems are getting cheaper and cheaper. We're not seeing rapid growth, but certainly every month there are, another 20, 50,000 modems out there. This is one of these things that's sort of creeping up on us, and most people have just sort of written it off, because the industry wisdom all this time has been, no, there's not a big enough marketplace. But that market is steadily growing. One of these days, somebody's going to go out on a limb and say, I'm going to do the killer modem game. It is great.
You got to know, Larry went out on a limb and did a killer modem game.
Did he lose his shirt?
No, I lost my shirt. It wasn't the shirt that was the problem. I lost something else. No, yeah.
I lost the company.
Oh, okay.
No, but you're right, though. I mean, we didn't lose the company, and we were unsuccessful for a lot of other reasons, not because the idea was invalid.
It could have been too soon. There's this fundamental question about when is the right moment. We know that it isn't quite yet, but we also know it's gonna happen someday. It may not be this year, next year, it may not be for 5 or 10 years, but someday that's gonna be a viable marketplace. Somebody's gonna come up with one dynamite modem game, and it's gonna blast off. It's just a question of who has the right time. You come out too soon, you lose the company.
I mean, we didn't sell tons of them, but I still get letters from people that purchased the games wanting to know like when more are coming out. And the people that did buy it really liked it, and people that were into that kind of thing.
Yeah.
There's an awful lot of variables involved with that. They're not just so much selling a modem game, but you've got a lot of variables that you have to consider, like 2 copies you need all of a sudden.
Yeah.
And there are a lot of game design. There are a lot of game design problems in that. To develop a modem game, it's very difficult to develop a one-player game as well as a modem game.
Yes.
There are an awful lot of problems that pop up, and our problem was we couldn't, or at least we didn't. We were fighting technical limitations at the time, and we put a lot of effort into that, and we ended up with a so-so game out of it. A good modem game, I would say, and not a very good one-player game. And that was our problem, because people wanted something to do other than just playing a modem game.
Yeah. See, your market problems, not only are you dealing with a subset of the overall market, i.e. the people who have modems, it goes as the square, because you're going to have 2 players.
With modems.
It's the square of a subset.
And that live fairly close together. But I will say this: in defense of the idea, I have yet to play. I've played a lot of computer games, and our modem game, I will not go out on a limb and say it was the greatest game ever. But the feeling that you were playing against somebody else at a different location, and he could walk across your screen and turn and wave at you, or the effect of the unknown, he could leave a bomb in a room, and you didn't know it, and you walk in and you blow up. The limited information idea.
Yeah.
Really works well with that.
Yeah.
And I think you're right. I think that's something that.
Well, especially knowing it's a person and not the computer.
Yeah, it's
Yes.
playing against it,
Yes.
and I get back to the characterization thing again. Is now all of a sudden that little guy walking on the screen has a lot more character than he had when he was being controlled by the computer.
You don't waste any time with artificial personality. You got the real thing.
In a confined universe, granted, but you've got that guy being controlled by another person, and it's an awful lot of fun.
The 2 experiments for this year in the telecommunications area, one is by Scott Lamb, I think, an Amiga combat game, tanks moving around shooting each other.
I played one of them called Firepower, which is like a capture the flag type game where you have you're in a tank and you got terrain and you blast through things, and the object is to find the other guy's fortress blast your way in and get his flag and then bring it back to your own
Yeah.
territory. You can see, if the other guy comes close to you, you can actually see his tank on the screen, you can shoot at him and all kinds of stuff. It's kind of neat.
Scott's is on the Amiga, and I think it's called Telewar. And the other interesting experiment of which I'm aware is Dan Bunton.
It's not three-dimensional.
Anything Dan does, you've got to pay attention to. This one has the execrable title of The Sport of War. This is the EA marketing gurus at work. But they saw, you know, Brutagund has this game called The Ancient Art of War, so we'll call ours The Sport of War. Woo! Anyway, it's a C64 product. So, yeah. And it could catch fire, or it could follow in the same steps.
Well, our problem was, I think, just money, lack of marketing expertise, and lack of leverage. You know, we're fighting big companies, Electronic Arts, Epix, Mindscape. It's very difficult to get distribution. It's very difficult to get shelf space. We had good response from the people we sold to, but our vast majority of our selling was through Canadian distributors. We had a couple Canadian and a small distributor here in the States, and it just wasn't enough to sustain advertising for such a cause.
Another big strength of the computer as a game technology, and also slightly somewhat underutilized, is its plasticity. That is, everything that you set up in the game can be changed. In a regular board game, hey, this is the board, you don't change it. In a computer game, if you have a board, you can change it anytime you feel like it. You can rearrange it, come up with a new board. You don't like the counters? Okay, we'll come up with different units. You want to make this unit stronger? Fine, we'll make that unit weaker too. You can rearrange just about everything you want. It's a matter of what kind of program you're willing to write. The more indirection you put into it, the more difficult it is, but you get more plasticity. Again, we haven't seen that, I don't think, fully utilized yet, but that is another nice capability of the machine. And finally, I feel the most important capability of the computer is its ability to provide an intelligent opponent, somebody who can shoot back against you, who is not a human. I'll say one thing about that right now. The embarrassment of victory or defeat. One of the real problems with playing a game with a human opponent is that either you win or you lose, and either way it's embarrassing. That is, you know, what happens if you lose? You know, well, gee, you jerk. Or I feel kind of stupid or whatever. It's just as bad if you win, you know, you beat the shit out of some poor dumb cluck. You know, gee, I'm sorry, I didn't realize you were that bad. I wouldn't have and it does get embarrassing. I remember when I used to play war games, getting a good opponent was always difficult. Because there weren't many people who played war games. And so you saw it high and low, and you finally, you'd hear through a friend of a friend that there's a guy they know who plays war games, and so you call him up, say, hey, I hear you play war games. He says, oh yeah. So, oh great, what kind of games you play? Oh, Risk? Yeah, I play Risk. And you pause and say, oh well, have you ever played any SPI games? What's that? And, okay, well, thanks, bye. And then you find another friend of a friend and call him up and says, oh yeah, I play SPI games. You say, well, then you want to get together Saturday? Yeah, sure. Come over to my place. Great. Saturday morning, you get the game set up on the table. You're all set. There's a knock on the door. You say, oh, good. You open the door. Sieg Heil! General Smith is here to beat your pants off! And, you know, he's got a German helmet on. You know, come on in here. This happened to me once, I'm not kidding. And it is really striking. The worst part of it is, you're sitting, well, okay, let's play the game. And you're sitting at the table, and then your wife comes home. And here you are with this guy, and he keeps talking in fractured German. And,
what's for lunch, dear? Blitzes and kosher salami.
Right. So, anyway, you got a lot of problems with human opponents. And the computer is so and then there's a problem. You beat the guy and he gets mad. And computers are so nice. They don't pull any of this crap. You can play anytime. You can beat the shit out of it. And you can say, "I beat you! Ha! Beat you! Ha ha ha!" You can't can't do that with a human. And if it wins, you say you can.
Well,
And if the computer wins, you say, oh yeah, click. And that feels just as good. So computer opponents have a lot of advantages over human opponents. The one problem is they're nowhere near as interesting as human opponents. They never do as the weird, strange, neat things that humans do. But with good programming, that's our job. If we do our jobs right, I'm convinced that we can right now produce decent computer opponents, and I think we can do a lot better than decent. I feel that my opponents have gotten, the opponents that I create have gotten better every year. And I'm now convinced I can produce, say in a wargame environment, I can produce a computer opponent that will play better than the average human opponent. So we're getting along there. So the computer has a lot of nice strengths, but it also has some weaknesses. And it's nice to gloat over the strengths, but it is crucial to be extremely aware of the weaknesses of the computer. And they all arise from I/O. All of the weaknesses of the computer are in its I/O capabilities. Every game establishes a language of interaction between the player and the computer. Not just every game, every application, every program that runs on a computer has a language of interaction. You've got the user over here, you've got the computer over there, and they're going to talk to each other. That is the essence of what's going on here. Whether you're talking DOS, Unix, the Macintosh user interface, a word processor, whatever, the human is sitting over here saying, this is what I want you to do. What do you have now? And the computer is saying, this is what I've got. Okay, I'll do what you want me to do. And the problem is that communication is frequently fouled up. The human doesn't know, how do I tell you to get this the way I want it? And the computer is saying, beep, beep, 101010, and what we have here is a failure to communicate. So every program, every game establishes this language of interaction. And the quality of that language controls the quality of the interaction. If you got a bad language, you can't interact. And that's where the computer fails over and over and over again. It's hard for the two of them to talk to each other. Now, with output, we spend a lot of time worrying about output, how the computer talks to the human. And there are problems there. In the visual area, resolution is too low. We want higher resolution. We want more color. We want animation capabilities. And we all know how desperately difficult it is to get really good visual imagery on the screen. We can always rig it so, well, I can give you either animation or color or resolution. But as yet, unless you're talking about an Amiga, it is very difficult to get lots of animation, lots of color, lots of resolution, all at the same time. We're always making plenty of trade-offs. That is a problem because we just can't say enough to our user to clearly show what's going on. Let me talk a little bit about trade-offs between these three. That is resolution. Question? No. Okay. Resolution, color, or animation.
Sorry.
You just bought $50,000 worth of stock.
Let's see. Resolution versus color versus animation. Here what we're really worrying about, normally we look at this problem as a question of what is the computer capable of doing, but let me turn the tables on you for a moment and talk about what the retina is capable of receiving, because that is, I think, the more important consideration, because the retina is biased in many ways. The retina's greatest strength is in shape recognition. It is very, very good at resolutional issues. And so resolution is should be your primary way of communicating. That is, the most important information going out to that eye should be shape information. If you're sorting, if you're saying, here are all the things I have to tell my user, and then you rank them. here's the most important thing, and then here are minor details. Communicate the most important things through resolution, through shapes. The second most important is, well, I'll say animation. And the third is color, but I'll immediately qualify that by saying animation is how you catch the eye. Animation is good as a flag waving thing. If you need, warning, danger, danger. Animation is good for that. Animation has some lesser value as just an information communicating. You want to indicate that something is changing. The best way to indicate that it's changing is through animation. If it's static information, then color or resolution, depending on how important it is. What I'm saying here is that color is, in general, the least important way of communicating, or the least effective way of communicating things to the retina. I'll qualify that observation with the counter-observation that affective information is best conveyed through color. Affective is emotional stuff as opposed to cognitive stuff. That is, if you want to get into their guts real quick, use color. If you're trying to give them information they need to think about, use shape and resolution. But color is a very powerful gut-level thing, and is best done as a background. That is just sort of a global, red screen versus blue screen versus green screen, that type of thing. You can still use color in many, many other ways. There's infinite room here for creativity. I'm giving you some general guidelines based on what I know about how the retina works. There have been studies on this, by the way. This isn't just random bull. There's some people at Xerox PARC who spend a lot of time studying this stuff. And there is some interesting stuff that comes out of that. One of the interesting things is when color swings in as a major communication element. And it turns out there's a breakpoint in the order of 10 to the 6 pixels. That is around 1 megapixel. Let me see how do I best explain this. Suppose you're a hardware designer and you're designing a display system. And your option is, and they come to you and they say, we've only got this much resource to put into the display. How are you going to divide it? You can either put all your money on resolution and get more pixels, or you can put some of your money on color and get fewer pixels but more color. How are you going to divvy it up between resolution and color? The general conclusion is that below a megapixel, you're better off putting all of your money on resolution. Resolution is more important than color, so long as you have less than 1 million pixels on your screen. Between 1 and 4 megapixels, it's a trade-off. Above 4 megapixels, you've saturated the capacity of the retina to absorb shape information. And you must start adding more information through color. So those are, and these are real soft numbers. Don't take those at all as hard and fast numbers. But basically, below a megapixel, black and white, and try to get the number of pixels up. And then once you get up into the megapixel range, then you can start adding color. Yes?
This is basically, this is for conveying information. That's the trade-off.
Yeah.
If this display is designed to convey information.
Yes, yes, that's what
Because-
all these studies are about.
Okay,
They're not
because-
about affective, because that, everything's up in the air when you talk affective.
Well, affective, yes, in terms of conveying emotion, but still, first display that I saw that was 256 by 256, not very great resolution, kind of primitive even compared to a Mac, but it had 256 simultaneous colors, looked gorgeous, conveyed. You take a Mac screen and have a picture of a babe, of a girl, of a woman, of a self-realized,
Whatever you want to call it.
that's right, girl, woman,
It's chick.
A babe, chick, girl.
a self-realized human being.
Thank you, David.
You're welcome.
It's from me.
On a Mac,
You are the only,
okay, added
you're the only babe
resolution,
in the room.
and you take a picture, okay, on a 256 by 256 screen, and forgetting their emotional content, I would maintain I get more information about this self-realized person in the color picture. It looks more like, it more represents the reality.
It's an
than
unfair
right.
comparison.
Okay.
If you want the comparison to be fair, let's use the same buffer. So we got a 21K buffer on the Mac,
Okay.
176 kilopixels.
Okay.
Okay, now let's talk about the equivalent. You want 4 colors, okay, let's cut the resolution in half. You want 16, let's cut it in quarter, so forth. Then, and this is exactly the type of experiment they did, although they didn't say how pretty does the girl look. They were saying, how much information can we communicate to your retina in 1 or 3 seconds of viewing time? And what they found in all of these experiments was they were most effective staying with pure black and white until they got up to the megapixel range. So,
But I'm just thinking that those studies are still conveyed in hard information.
Yes.
Figures,
yes.
You know.
numbers, text.
well, they,
Editing type activity.
no, it
screen
wasn't
layout.
just figures, numbers, and text.
Okay.
They were trying to.
Graphic.
They did a variety of things. Just how well can we present information in general? Because obviously, if you're using text, it's biased.
From what I understand, I mean, basically the same types of studies were done at the advent of television, on the NTSC standard and things, where that's where they agreed to go with more hue and saturation, whatever, of the television as opposed to the resolution. The same thing. And
Well, the
those
television
seem
is
to have come
way
to
up
different
there.
conclusions.
No, because it's way up beyond a megapixel.
Okay.
So it makes sense in television to put a lot more color into it. I'm not sure where you are, but you're way up. You're way beyond 4 megapixels on TV. I don't know.
You get unlimited range of
255
colors just about.
Yeah, but I know they weighted heavily with, you know,
It's like
colors
500 by
and
500.
variance in color over the actual pixel.
There's some hardware guys who are going to
Yeah, what is the resolution of?
Yeah,
it's funny
video
people.
lines.
You get 525 lines, but I don't think you get much more than 500 effective. It's analog, so it's hard to compare.
Yeah.
The resolution across the screen, which translates to like 800 pixels, because the definition of the line is different. They say that you can recognize lines, actual vertical lines.
Yeah, that's right. That's the way they did it.
So, it
So
would
that
be like
comes out pretty
800
low.
horizontally and 500.
What are 800 by
8 by
500?
500.
Yes.
Okay, so that's only 400 kilopixels.
Yeah.
Right.
Yep.
So I'm just
So-
trying to, I think there's a difference of information that
Yeah.
they're both trying to convey. I mean, Xerox PARCs, I imagine they're working on their workstations, you know, and how much can we feed back to people as far as icons and things,
Yeah.
as opposed to realizing real life pictures,
Let's just
where pattern recognition is quite as,
take the Commodore 64, for example. That has 2 graphics modes, a high resolution bitmap mode, and it's multicolor 16 color bitmap mode with half the resolution.
Yeah.
Yet typically any arcade game done on the Commodore, any game is done with the 16 colors.
Yeah.
For sake of the you know, typically.
Well, I know that in that regime, when I used to work on the Atari, the reason my personal experience that I used to back up that rule is that when I was working on the Atari, that had lots of color and was down in the 64 kilopixel range. I spent a lot of time worrying about resolution. I could never get enough pixels on the screen. Color, I always had plenty of colors. I remember one display I set up, I initially set it up with a lot of colors, and then later on I came back and I said, I just can't use all those colors. And I took colors out. It was just loud. It wasn't any clearer or more informative.
Again, well, that's a less cut and dry
So-
situation.
Yeah, well,
I mean,
that's down
you've
in
got,
the real
here
low
you've got you either want your
range,
64
and it's easy.
kilopixels with 2 colors, or your 32 kilopixels with 16 colors.
Yeah,
Well, obviously the choice has been the 16 colors over the resolution.
yeah.
It's just a little bit of an interesting thing compared to what you're saying. I'm not saying that what you're saying is wrong. It's just a difference of approach.
I think it makes a lot of difference whether you're trying to realize realistic type images, you know, as opposed to board game or, you know, icon type images too, where there are lots of colors just conflict after a while.
Well, in any event, there are trade-offs to be made between color, resolution, and animation, and it is important to take the time to organize your graphic presentation with those things in mind. That is, what am I going to try to convey through resolution, what through animation, and what through color? Just sort of rushing into it and saying, let's just do lots of neat colors and lots of graphics and lots of animation. You know, graphic presentation must be thought carefully about. Some things are better presented through different styles. And then, of course, on output, there's also the problem of sound, which is difficult to do. You can sweat getting a good sound effect, and even if you do get the sound effect exactly the way you want, then the damn thing eats up 20K of disk space or something like that. It is very, very difficult to get the sounds flooding out the way you like, so we end up pulling all sorts of stunts to compress them and reuse them, and we'll play this one backwards, and all very, very difficult stuff. So it is difficult getting the computer to talk to the human. It is much more difficult allowing the computer to talk to the human to talk to the computer. And at this point, I want to point out a fatal weakness in many, many game designers. It is the failure to realize that this language of interaction is fully bidirectional. That is, in one of the JCGDs, I did an article called the interacting circuit or something like that. The basic idea was this is not a situation where I and the computer am doing all the talking and you're just dribbling a little back. The quality of the interaction is like current flowing through a circuit, and you want as much current flowing through that circuit as possible. And I very much believe that most game designers put a lot of energy into how I'm going to talk to the customer, and, well, if he wants to talk to me, that's his problem. Very little energy into what he gets to say coming back. And so, oh, we have glorious graphics going out to him, and boy, the sound is really neat going out to him. And what does he get to say? Up, down, right, left. And that's all. So we end up with a really lopsided loop where tons of information is going out and very, very little is coming in. Now, part of that is unavoidable. Let's face it. How much information can you put up on a screen? A hell of a lot. You can change it every 60th of a second. You can really pump it out. And if he's got a joystick coming back in, well, how fast can you send ones and zeros down a joystick port? It's just, even at your very fastest, you're not going to be able to put that much in. By the way, this is a slight digression, but I wasted about a month or two at Atari Research analyzing joystick patterns. That is, we wrote an eavesdropper program, and we just took a joystick and put a Y on it. And so we had two Ataris set up, and one was set up with a game, and the other was set up with the eavesdropper program, and then you just play the game. And the eavesdropper would just keep track of how often the joystick was being used in different things. And then we analyzed people playing different games on it, trying to find out what they were doing, and we analyzed the information content. And what we did find some interesting things, namely that in really good things, the information content coming down that wire was pretty high. That is, the player was doing things with the joystick a lot. Whereas in bad games, the information content would be spotty. That is, it would either, a lot of leaning on it to the right, and then a long pause, and then a lot of leaning on it to the left, and the net, what is it, there's a coefficient that allows you to calculate how much information is coming down. That would be very low. So if you think of the joystick as a device that emits bits, how many bits are actually coming down that wire? Not very many. It's a bad input device. But what do we have instead? A keyboard? With a keyboard, you can say a lot if you're a fast typist, but it's still hard to say a lot with a keyboard. A mouse is a better input device because a mouse is tied intimately into the screen. And so theoretically, a mouse lets you say an awful lot of things very quickly. Basically, I wonder if I should go into this lecture here about the expressiveness of input devices. I'll give you a brief synopsis of it. You have a scale here, and at this end of the scale you have a push-button switch. Its expressiveness is 1 bit, either on or off. And then the next thing up is a joystick, which has an expressiveness of, 2 or 3 bits, if you count the trigger. And then we move way up to a keyboard, which has a net expressiveness of 5 to 8 bits, depending on how many keys are on the keyboard and the shift functions and so forth. And when you look at that, you'll observe with this choice, oh, let's put one other in here in the middle, a keypad. 16 key keypad, something like that, which has an expressiveness of about 4 bits. Now, when you look at that spectrum, you see the rule that, gee, the more expressive devices, those are great. We like to be more expressive, but the reaction times on them are much, much slower. That is, the single button input device, you could do a very fast reaction time game on that. You know, push the button when you see the bad guy. Boy, you can get real fast reaction times. Joystick is a smidge slower. Keypad is a little slower still. Why? The user has to hunt, find the button he's going to push. And there's more latency time because he's searching a larger space. Keyboard is searching a huge space to find the key he wants. So, unless you've trained him, that's the trick. If you've trained him so he doesn't have to search, he knows, you know, he's wired it into his cerebellum, that's where K is, then the search times are low, but you need those long training times. So there appears to be this horrible trade-off. If you want a lot of expressiveness in your input device, then you either have to have a long training time, you've got to expect low input rates. And so the horrible conclusion seems to be that no matter what, the bandwidth of information flow from the user to the computer is always going to be very low. And one thing that sneaks around that is the mouse. Because the mouse, theoretically, has as many options. The mouse can be way out here. How many bits do you have in your screen display? That's how many options the mouse has, because theoretically the mouse can click on every single pixel, and every pixel is different. Now, yes, it takes a little longer for him to do that, but because of that visual loop, you are you get a big savings here, and so the cost in seconds, in time, per bit of selectability is very, very low, and so you get this huge leap with a mouse. Still, you are required to go to a mouse-based system for this to work. What really makes the mouse neat, from my point of view, is the fact that the mouse can be rigged as a plastic input device. That is, all these other devices, are the number of bits they select are fixed, but a mouse, you can rig it up on the screen so that in this case, it's a 1-bit device. Just click to acknowledge. In that case, it's a 2-bit device. Pick one of these 4 options. In this case, it's an 80-bit device. So it can be as many bits as you need for the situation. That's the real strength of the mouse. Even so, it's still a clumsy input device. We have a very serious problem getting input in a machine. The primary problem is that the primary modes of human expressive output are simply not suited for computer recognition. Here I am talking about, you know, a joystick where conceivably you can do about 2 bits every few hundred milliseconds, so we're talking maybe 10 bits per second worth of input. That's the bandwidth you've got on a human talking through a joystick. Well, let's compare that with just straight human expressive capabilities. Suppose, here I am talking to you, right? What are the modes with which I'm communicating? Okay, I'm using voice. How much resolution do we need to fully understand? Well, you know,
7
yeah,
7K.
Yeah, if you want to get the voice intonation, you're going to need to go up
56 kilobits per second.
Okay. So, you're going to need, that's a lot right there, just for voice with intonation. But wait, there's more. What about all these hand gestures and this body English? You're going to need a lot of bits for that. Now, of course, hand gestures are pretty gross, so you're not going to need the exact position of everything. You're going to need a goodly number of kilobits there. And then let's throw in the human face, because that is immensely expressive. There's a great deal of information that comes out through the face. In order to properly show the type of stuff coming in on the face, you're going to be needing to digitize at a pretty good resolution. I would say to show a face well, you need at least 256 by 256. And you're going to need to be sampling that every 100 milliseconds, because facial expressions can flash by very quickly. So what kind of baud rate are we talking about there? What I'm saying is that the human expressive capabilities are gigantic. I can put out information a lot faster than a computer can. You know, we talk about, well, it can, you know, at the very fastest, you're pumping out tons of information on that screen. Human can beat it. Human can say more faster in terms of just raw information. So our problem is, so imagine human beings sitting here capable of pouring out rivers of information. And what do we hook him up to? A joystick. This is like hooking a fire hydrant to a straw. You know, it is a real crime here. We are not getting anywhere near what we could be doing. I see this as the fundamental problem in computer game design right now. This is far, far more important than any of the problems with graphics and sound and so forth. Yes, it'd be nice to get those things going. But right now, the human can't even say anything back. Now, there is a school of thought that says that doesn't matter, because people are basically passive slobs. They don't want to do anything. They just want to sit there and be entertained. So who cares what they have to say back? And as you might imagine, I don't think much of that line of thinking. So
that's the couch potato thing.
yeah. And Tom Snyder believes in that, and Brenda Laurel believes in it, and I don't. I don't think people are couch potatoes. So anyway, let's see.
Yeah, just be. I went to school with Brenda. She graduated from my class.
Brenda Laurel? Oh.
It shocked me when I found out she was in the industry. I've been seeing her in 10 to 12 years.
And David believes in couch potatoes.
Yeah. It's just a shame that interactivity is the computer's greatest asset. Because couch potatoes could care. They're still struggling with the remote control. I'm a cynic.
Well, maybe if they could just say, change the goddamn channel, and the TV would say, okay. You know, then it wouldn't be the problem. It may not be with them, but with the damn remote control.
Find some wrestling.
Yeah.
Find some wrestling. Oh, no, find some wrestling. With women.
Or you can walk up and say anything but Howard Cosell. So, anyway, we have a severe problem there. This is a fundamental weakness of computers. It is very hard to get the computers to be able to talk to a computer well. The solution, I feel, lies in linguistic approaches. That is, ultimately, we know someday, if you go far enough in the future, and you imagine people working with computers, they're not going to be sitting there with keyboards. They're not going to be talking to computers. That ghastly scene in Star Trek 4 where Scotty sits down with a pen and starts typing at 100 characters per second. If this were real, he would have held it up and said, "What's this?"
You tried.
Yeah, okay. Well, that was with the mouse.
Computer?
Yeah. Right.
Oh, shit.
Ultimately, people are going to talk to computers. That is the only natural way for them to communicate, because that's the way we communicate with each other. So, yes.
Wait a minute. Now hold it. I draw the line right there. That's bullshit. That's like the saying that Dan Sandine worked forever on inventing what he called the Wonder Glove. There's a lot of talk about the grabber now at this point, but the fact is, all you're looking for is a way to push a button. God made a great way to push a button, which is brain, nerve endings, finger, a terrific aiming device, and all you need is a button. Bang.
If all you want to do is say one bit of information.
That's fine, but my point is there's nothing natural about talking to a computer in English language. The fact is, the keyboard has been a damn good input device up till now, and you're just talking about real time. I would rather customize the input and use a remote controller that gives me fast, easy access through my fingers, which are agile and take a minimum amount of training, than pay for the enormous amount of, overhead that would go into worrying about whether the computer is going to understand what I have to say to it. There's a tremendous amount of misinformation that goes on between people talking. I certainly don't want to trust a computer to try to understand what I'm saying to it.
Well,
I mean, I think there can be appropriate devices for machines other than natural language that will perform better.
the problem is bandwidth. How are we going to get enough bandwidth to be able to somehow communicate complex things to a computer? If all we want to say is, here's a button that means nuke the world, one bit of information, do it or don't, then yeah, sure. If all we want to do is send, here's a character, 6 bits, 8 bits, whatever, push the button. Fine. But if computers are going, I'll just talk about games. If we're going to have games where you get to do a lot more interesting things and get involved in deeper interactions, we're going to be communicating more information to the computer. We're going to be saying, here I am playing this computer game, and I'm saying, did you know you have beautiful blue eyes? And, you know, seductress comes back and says, oh, really? Yes, that's very nice. If I'm going to do that, I want to be able to use voice intonation. I want to be able to use language. I want to be able to communicate far more information.
If you're doing a human being simulator, I mean, because that's what you're talking about. If you're doing a flight simulator, you want to have controls that are as much like the control panel of an airplane.
And if I'm doing word processing.
But the point is if you were doing a flight simulator, all I'm saying is that, you know, obviously you agree with it, and you wouldn't want to, you know, talk to the machine.
Agreed. Agreed. I still
lambs.
But give it some
maneuver.
Have you seen? There's a product out now that comes with a little microphone. It's a C64 product. For $35, you get the microphone headset too. Well, the only thing, it's one bit of information. It's either cough or not cough, and it's tied directly. All it discriminates is fire.
I didn't mean to fire.
Just says fire.
Wait.
So you have the bullets right. Anything you say, anything causes it to shoot missiles out. You cough and it shoots missiles out. You're pointing at your own base.
That's basically what you're saying.
Perfectly
But given someday that a computer can recognize human expressions.
No, but wait. I understand what you're going to say.
Right?
And,
Would you not want to go with that?
No, wait.
I know what you're
Was it the facial expressions that made you know?
No, I know the argument's coming because I didn't address it. No, grant the technology, because I was making it sound like I was concerned that the computer couldn't do it, which they really can't very well now. But let's say grant the technology. A computer can understand you as well as a human being, and God knows we can't expect them to understand any better than human beings understand.
Agreed.
I'm sorry, it's like I said, there are many situations where I'd rather address a machine through an unambiguous input channel than I would talk to a human being. For instance, I would rather type my own manuscripts than dictate them. I will have fewer errors if I do the typing myself. Even as far as not even talking, typesetting. In typesetting, I'd much rather do my own typing and telecommunicate it than I would type it, do a copy, and have it go to somebody who has to read it and type it in. And that's even less ambiguous than speech is. So I'm just saying that I don't think speech is... If you're doing a human simulator, I entirely agree with you.
Put a tree here. Well, what's a tree? You know, it's like, you couldn't do it.
On this input device thing, I will bring up a war story. Have any of you ever heard of the Atari headband?
Yeah. We all saw it. We're just waiting.
I saw it at the show. I just loved it.
Oh wait, you're talking about the recent.
No, this is way back.
Okay.
Yes, way back when they used to have big booths.
And do you
Go back.
do you know why they abandoned it? Did you hear the denouement of that
So
technology?
kids' faces permanently got like that?
Somebody would slap you on your back and you were playing with the machine and you were in trouble.
No, the problem was that it worked. It did pick up the brainwaves that it was looking for. The problem was people immediately found that when they'd get excited, they wouldn't use brainwaves. They'd be using muscles. And, you know, you get a little electric potentials just by straining your muscles. And so they start getting excited, and you're like this. And then after it was over, people would take it off and say, oh, what a headache. And that was the end of that technology. So anyway, we do have serious problems getting input into these devices. And that, I feel, is the greatest weakness of the technology for game design. So, I'm now going to change the subject. Maybe, let's talk a little bit about time schedule. Oh.
Can I ask one more thing on check? Because I'm not even if you had that bandwidth, or even some portion of it, let's just take the joystick bandwidth. Computers still, I mean, maybe it's just a lack of our software cleverness, aren't so very hot at pattern recognition. Even at the level of joystick pattern recognition, I don't think we were even doing what we could do with it.
Yeah.
So, I mean, let's assume you get rid of the straw and replace it with a decent-sized garden hose.
We'd still have
What the hell are you going to do with all this water?
Yes, you're right.
The minute you get rid of that problem, you'd have now a Macintosh sitting there. Well, I'll process this for 4 hours. I'll be back on your move.
Yes, yes. I mean, we could have a microphone input, and the Mac would take several hours digesting.
I mean, is it the bandwidth that's a question, or just input devices that are more tailored to the needs of the program? I mean, for example, now like these the fighter pilots these days, apparently they're able to move their heads and steer the craft with that sort of input device.
Yeah.
I'm not real familiar with exactly how that works, or if that's even realistic. But I mean, it seems to me that you need input devices that are more hardwired to a given application, a given set of circumstances. And there's not necessarily, I mean, a joystick doesn't lend it. I mean, missile command with a joystick wouldn't have worked. Missile command with a trackball did work. Give it an input device that is tailored to an application. And I don't necessarily believe that bandwidth is as much the problem as just we have just one generalized input device that we try to make work with every computer game that we've ever done.
Well, let me simply make the observation that the bandwidth of input right now is measured in, 10 to the 1 bits per second, typically. The bandwidth going out is, 10 to the 4 bits per second. In that imbalance is much to think about. What does that mean about the nature of gameplay?
Well, what about the game player itself? I mean, you look at Defender that had joystick up, joystick down, thrust, fire, left, smart bomb, hyperspace. You had 9 buttons in front of you, and most people are just acclimated. They're good at 1 bit in, 1 bit out. They couldn't handle that.
Well, partially that was because of the alien nature of it. See, the input devices are all designed for the convenience of the hardware.
I don't think so. I don't think the player. I mean, that's why people have automatic transmissions. You put it in drive and the car goes. I mean, clutch, shift, gas. I don't think the average person's gonna get into too many.
Well,
more to the point, just perceptual. When you're talking about what's going in, what's going out, you're comparing apples and oranges. Because what we're getting out to a visual display. The eye processes tremendous amount, huge number of bits of information. You all know this, and it needs it. It requires it. So, if we were trying to communicate with the computer visually, it might be a different thing. I mean, if we talked to a computer through a TV camera by showing it pictures, then I think you'd see the I/O starting to match up, because that's what you're dealing with.
Yes.
I mean, you don't have a visual input, and that's why you have this huge. I'm not disagreeing with you in terms of how games have been designed and how much information has been back and forth. But I do think that comparing, the bit resolutions of input versus output, you've got to be looking at what media you've got there.
Oh, this is an awfully clumsy way to analyze it. What I'm trying to do is give you an idea of the magnitude of the disparity. When we look at these two devices, human and computer, confronting each other. The computer sits here capable of putting out maybe 10 to the 4 bits per second, capable of taking in maybe 10 to the 1 bits per second. The human sits here capable of taking in, 10 to the 7 bits per second, capable of putting out just as many bits per second. How do these two things mate? Very poorly. And the worst mismatch is right here at the bottom. Humans putting out 10 to the 7, computers taking in 10 to the 1. We got a problem here, folks. Now, this is one of these long-term, centuries from now, maybe we can talk about a solution. Right now, we don't have a solution, but it's at least something to keep in mind as a theoretical issue. So, first let me ask some questions about schedule here. I'm ready to begin a rather intense section here. We could take a break now, and then I'll do the rest of it in one big flying leap. How does that sound? Okay, 10-minute break.
At least you're around the building.
Yeah?
The heaviest idea I have to present here, and therefore the most theoretical, and therefore the easiest to dismiss as bull, but I think it's the most important idea I've got to say. So let me get to work on it, and I call it process intensity. What does a computer do? It does data processing. And the challenge I put to everybody is, when you think of data processing, processing? Do you think of data or do you think of processing? And of course the clever answer is always, well, I think of both of them equally. And if so, that's wrong. Because data is very minor. The important thing about what a computer does is processing. Processing is the very essence of computing. And therefore, good computing is process intensive. It concentrates, it puts its emphasis on the processing, not on the data. Now that may seem dumb, but there are all sorts of implications of this, and there are a lot of games that violate this rule, and they come up looking dumb like this, and a lot of people who've lost millions of dollars because they failed to keep this in mind. Now, let me describe exactly what I mean by process intensity and data intensity. Processing is crunching data, taking numbers in and doing things to them. That is, taking numbers, adding them, subtracting them, multiplying, dividing, logical anding, oring, logical exclusive or, somehow crunching the numbers. It's not the same as just shuffling numbers. If all you do is just take numbers in off the disk drive and move them over the screen and take some numbers from the keyboard and move them over the printer, if all you do is shuffling bits around, that's not process intensive. That's just shuffling bits around. So process intensity emphasizes crunching numbers in interesting ways. Now, I will immediately point out, yes, you can do idiotic processing. You could write a program that has a random number generator, takes in a piece of data based on the random number, either adds it or subtracts it, and then puts in, prints the garbage out to the printer. And yes, you can do that, and yes, that's stupid, but the idiocy of that arises not from the fact that you're processing, but from the fact that you are processing idiotically. So the fact that you can abuse something doesn't mean that it is bad, that it is intrinsically bad. When people look at programs, there is always a mix of data and processing, and there are a number of common fallacies. See, there's a common problem we encounter. We lean towards data intensity because it's a lot easier to write a data-intensive program than a process-intensive program. Why? Data is tangible. I mean, you can get your hands, if you've got an image, once you've got that digitized, you've got it on that damn disk, you've got it. That image is there. You can, if you want, you can put it up on the screen here, you can put it down over there, you can convert it, you can change the colors, you can do all sorts of things to it, but you've got that image. It's something you know, you can understand. You got a number. Now I know what that number is. It's tangible, it's direct. Process, that's intangible, it's abstract, it's esoteric. Let me give you a specific example. I will use the whiteboard for once. Is this safe to use on the whiteboard?
Hope so.
Okay. I can tell you that the distance from the Earth to the Sun is 93 million miles. There's a number. Wow, I know something now. I've got it. This is a fact. This is truth. Hooray for me. Or, have you ever heard of Bode's Law? An astronomer around 1805, I think, came up with this formula. I don't even remember it, but it's a simple linear thing where R equals, I'll just make up numbers, 0.6 plus 0.3 times n. Oh wait, maybe it was 0.6 plus 0.4 times n. There's some simple linear formula, maybe some a little more complex than that. There's a formula for the distances of planets from the Sun. Take the planet number, plug it in there, and bingo, you've got the distance from that planet to the Sun. Maybe it was minus 0.6, whatever. Anyway, the idea was you just say Mercury is 1, Venus is 2, Earth is 3. This obviously doesn't work. Mars is 4, and so forth. And bingo! Calculate the distance from any planet to the Sun. As it happens, this is wrong. It doesn't work anyway. Bode was wrong. But the important point I want to make is that I can give you data, or I can give you an equation. This actually says a hell of a lot more than this does. This just tells you one little fact. This is a process. In order to use it, you have to plug in numbers and turn the crank. But it gives you a lot more. It tells you more about the universe than this does if it were right. Yet, you don't get the same sense of pride and confidence in this that you have in this. And this is something you can take home and say, golly gee, guess what I learned at work today? The distance from the Earth to the Sun is 93 million miles. Isn't that wonderful? But this, what does this mean? Well, it's kind of hard to tell. Kind of hard to figure it out. This is direct. This is indirect. This doesn't, by itself, it tells you nothing. It's only useful when you do something with it, when you process with it. So, psychologically, we feel better about this type of thing. We feel more confident about data. And so we tend to lean in its direction. It's easier to work with. And so a lot of programs end up being more data intensive than they should be.
There's one other issue. Much easier to debug.
Oh yes, yes. This, I mean, you start writing, a process is what you do with algorithms. When algorithms screw up, it's a transitory thing. You got to catch it in midair. That's murder. If you do it all in data, it's just a matter of scrolling through static stuff. So, in every way, data is a lot easier to work with. We prefer to work with data. The only thing is, that's wrong. It's not right for the computer for a variety of reasons. The first and most important is it's an abuse of the technology. We have a zillion technologies for handling data. You want to store data, or not handling, storing. You want to store data? Great, here. You want to store text, paper, and ink. It may not be high-tech, but god damn it, it's efficient. It's cheap. It's a great way to store raw text. It's random access, maybe not machine-readable, but human-readable. It's a wonderful technology.
Portable.
Yeah, microfilm, microfiche, videotape, audio tape. We got a million ways to store data. Lots and lots of technologies, each with its own optimum range of applicability, where depending on how machine-readable you want it and how human-readable you want it, and the cost per bit and how instantly accessible and so forth. Depending, no matter what your circumstances are, we have a data technology that'll do it pretty well. The computer is not a data storage technology. The computer is the only technology we have that can process data. Accordingly, if you have all of these technologies for storing data, and one and only one technology for processing, how smart is it to use this processing technology for data storage? It isn't very swift at all. The computer should be used first and foremost for processing. Now, I can actually take this concept, make it a little bit more clear. So far, I'm talking all this fuzzy theory here. I can be a little bit more specific than that. I'm going to introduce you to a criterion for quality software, which I will call the crunch per bit ratio. And that criterion is obtained by simply asking, for any given program, if we were to somehow, if we were able to look at each bit of data, and when I say data, I mean numbers, images, sound, whatever. If we take, I don't want to say each byte, because I don't want to be quite that specific. But let's just say each chunk of data, each individual piece of data. So one number I'll call one piece of data. And if we then ask, how many operations are performed upon or with that piece of data? How many times is that piece of data manipulated? That ratio, the average number of operations per datum, the crunch per bit ratio, that ratio is an index of how good, how useful, worthwhile, good the program is. This is a figure of merit for software creation. Now that's a pretty wild claim, so let me start applying it in some examples. And I'll give you, I'll start with word processing. Let's imagine a word processing situation. You're going to write a book on Unix, let us say. And let us say, just for purposes of argument, that you know everything there is to know about Unix, and you're going to write a large book. And let us say that you also happen to be a perfect typist, and you are able to compose the book on the fly. with no flaws whatever. So you sit down one day in front of your word processor and you start typing. Theory of operation of Unix. Complete reference to all commands in Unix. All operands. All arguments. Typing. Variations on Unix. Subsystems of Unix. Complete program listing of Unix. Religious implications of Unix. You're typing away and out in these huge documents coming out. No mistakes whatsoever. You get the thing done. Typed all in. Here's this manuscript. And you ship it off. Why did you do this on a word processor? You could have done this on a typewriter. You have wasted a perfectly good word processor. You have wasted electricity. You've burned out your phosphor, you've worn the machine, all to no end whatever. This could just as well have been done on a typewriter. Why? Well, how many operations per data do you have here? Basically 0. Nothing was manipulated. You typed a key, then it went to the printer. Well, okay, maybe you typed it, went to the disk, and then it went to the printer. But basically, there was no real manipulation of the data going on. So the crunch per bit ratio was 0, and the utility of the word processing program was 0. No crunch per bit, no utility. Okay. Let's just say your publisher calls you up and says, Joe, we got a problem here. Unix is not spelled E-U-N-U-C-H-S. You go, oh no. I need to do a global search and replace. All of a sudden, so you go back, you did save it on disk, you go back, you do global search and replace. A lot of times, too. You can imagine a book on Unix, you're going to need to do a lot of replacements here. All of a sudden, you're saying, boy, I'm glad I did this on a word processor. Can you imagine going through with, white out and little placement? Boy, that would be a job. And so you're saying, now this word processor has really proven itself worthwhile. You will notice also the number of operations per data has gone up. Not a whole lot. You have actually manipulated a lot of data. Not nearly every word. But you've also reshuffled, the placement of the words on the line because now it's a little shorter and so words move up in the paragraph. So everything did get manipulated quite a bit as the thing got reformatted. So you did have a lot of operations per data. And that word processor was really worthwhile. But now, let's say, publisher comes back and says, we found a lot of errors here. The theory of operation is just plain wrong, and you've got some number of mistakes here. You're going to have to go back and rearrange this. So now you go back, and you're ripping paragraphs out here and putting them over here, and rewriting other paragraphs, and you're really working the thing over. And you're telling yourself, I am really glad I did this on a word processor. Because this would have been hell. Absolutely. I would have refused to do this on paper. But it was possible because of the word processor. So now the word processor is immensely valuable. And look what the crunch per bit ratio is. It has gone way up because you're doing a lot of manipulation. Still pretty much the same data. You're not entering that much new data, but boy, you're rearranging it a lot. Operations per datum are going way, way up. And the word processor's utility has gone way, way up. So the utility of that program is directly, well, I can't claim directly proportional, but I can say monotonically increases with the crunch per bit ratio. It's not just word processing, too. It applies with other applications. Spreadsheets. What's the point of using a spreadsheet if you don't play with it? That is, if you come in with a spreadsheet and you just type in, well, here's how much we're spending here, and here's our marketing budget, and here's what we're spending on production, and here's development, and new product cost. You add it all up and you say, oh, well, this is what we're going to spend this year. Okay, you take the number and you go walk off with it. Total waste of time. All you did was type numbers in, you didn't manipulate them, crunch per bit ratio 0. You could have done this on a pocket calculator. You didn't need a spreadsheet program. However, if you come back and you say, oh, I'm going to fire that Claude over in shipping. And shipping will be a little understaffed. Our shipping is going to cut by 10% this year, so this month. Let's change that. Shipping goes down. I think I'll increase the ad budget by 20%. Just change that, recalculate everything. Oh, and what if we buy out IBM? How will that affect it? recalculate, crunch, 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 crunch. The more you go back to that spreadsheet, and I haven't given you any ideas, have I?
No, Richard wants to buy even something.
Oh,
It's lofty goals.
It'd be a leveraged buyout, I'm sure.
I'm sure.
Anyway,
Come on, Lever.
the more you go back and crunch that data, the more you change and play with the numbers in the spreadsheet, the more useful the spreadsheet is. So again, the more operations per data, the higher the crunch per bit ratio, the more useful it is. DBMS, database manager, you would think. Now here is a data-intensive application if ever there was one. But we get in the same story. Suppose you get your DBMS. What's the first thing everybody does when they get the very first DBMS at home? They make a mailing list. Okay, we're going to send our Christmas cards out on a mailing list. And the problem is, who do you put on your mailing list? Your relatives. Now there's a difficulty here. You see, your relatives don't change. They're the same people every damn year unless they die or something.
Delete 12.
Yeah, but so there really isn't that many operations. You type in Uncle Joe's name and his address and so forth, and there really isn't much change. He just keeps on being Uncle Joe year in and year out. And so you're not really manipulating Uncle Joe or anything. You're not changing it.
Well, if he moves, then you have your address change.
That's true. That's true. So you do have a little bit. But basically, a mailing list of your relatives is not really a very useful mailing list. Now, if it's a mailing list of your friends, that's a little more useful because every now and then, get lost friend, whatever. Mailing, maybe your, swinging bachelor, whatever, mailing list of, girlfriends or whatever, something like that. That changes a lot. So you can have a lot more flexibility starting to get more useful. Now let's suppose this is a mailing list of people you do business with. Now all of a sudden we're starting to actually do something with this list. As in, oh, we've got to bill this guy for this much, and we got a payment from this guy, and now we've got a relational database, and we're going to link it to our accounts receivable and link that to our accounts payable. Now all of a sudden we're doing something with all of that data. Now that DBMS is starting to get worthwhile because the operations per data are climbing up to a reasonable figure. So even what you would think to be a data-intensive application is not. Its value arises from the processing of the data, not the data itself. Let's see. This also works in a negative way. Back in the early days of the personal computer revolution, we had two very special types of programs. You've heard of vaporware. Well, there was another type of software in the early days. It wasn't called this, but the most honest term for it was bullshitware. The first of these was the fabled checkbook balancing program. The idea here was, I want to buy this personal computer. I want to get myself an Apple II. Say it's 1979. I want to buy myself an Apple II. How am I going to convince the wife that we ought to lay out $2,000 for this thing? So we go home and say, well, we can use it to balance our checkbook. See? Bullshitware. And wife didn't know what we're talking about. Well, okay, honey, I suppose so. So, ha-ha, I get my $2,000 toy. And I don't want to say these things were vaporware. They really existed. There were quite a few checkbook balancing programs floating around. And everybody, when they got their Apple II or their Commodore PET or their TRS-80, everybody bought a checkbook balancing program. And they tried it out for about a month or so, and then they threw it away. Because they were useless. Why? Look at the crunch per bit ratio. What do you do with a checkbook balancing program? You type in the amount of the check, and then it is either added to or subtracted from your balance, and that's all. One operation per data. That's better than zero, but it's still pretty damn low. And so checkbook balancing programs never took off. They never worked. We are seeing a resurgence of them now, only they're not called checkbook balancing. They're called personal financial management programs. And actually they're much more than checkbook balancing because they'll group them by type, and they help figure your taxes, and they do a lot more stuff with those checks. They do more operations per data. And so they are more useful. There's still some question whether they're good enough, but they are more useful than the checkbook balancing program. The other bullshitware was the kitchen recipe program.
Yes, that's I just have to say back to
Okay,
Tim.
yes.
My favorite though was the atom, because you had to put the atom on your entire counter, and then you never cooked anything anyway. No room.
Yes, aside from the problems of flour in the disk drive, the real problem with the kitchen recipe program, even though these things were written, they were never really very useful because, again, I mean, you type in a recipe that says, you know, use 3 eggs and 2 tablespoons of flour and so forth. But how many times do you actually crunch that data? The only time where you really had any, I mean, basically all you did was you wrote it down and then you read it back. You can do that on a 3x5 card.
That's right. You get married, your mother gives you your cards, have a nice life, right?
Yeah. There was one case where there were operations per day. And that was when you said, I would like to make this dish for 3 people instead of 5. Right, right. And the computer would come back and say, yes. The computer would say, please add 1.73 eggs. And here's somebody with a knife and measure. So it never really worked. So, but people didn't understand, you know, everyone knew that programs didn't work, they weren't any good, but nobody knew why. Well, here's a good theoretical reason why checkbook balancing and kitchen recipe programs weren't really very practical. The crunch per bit ratio stank. This also works beautifully with games. The crunch per bit ratio explains both good things about games and bad things about games. First, it explains why games are such a popular application. Even with Apple saying, the Macintosh is a serious business computer and there will be no games on the Macintosh. People keep coming out with more games for it and they keep playing on it. Despite all of this resistance, people keep using games on them. One reason why is that games are ideal applications of programs because most games have fantastically high crunch per bit ratios. Consider a flight simulator, even though it isn't officially a game in the Chris Crawford official list. You're sitting here putting in your lousy 10 bits per second, telling it, well, you know, here, a typical game might look like this. You know, left, right, down, left, up, 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 up. That's the end of the game. But you're only putting in 10 bits per second. But think about the amount of crunching that's going on. It's recalculating all the aerodynamics, bank, lift, altitude, velocity, doing an enormous amount of computations based on those very few bits that you put into it. In other words, very little data going in, lots of operations acting on it. Very high crunch per bit ratio. So, let's see. You can also use this to explain why some games are dismal failures. And the best example, I love to pull this one out, video disc games. Summer 1983, Dragon's Lair hits the streets and creates an instant sensation. Everybody looks at the fabulous graphics in this game and goes gaga. The press goes gaga. The industry goes gaga. Atari initiates 5 video disc game projects. We gotta get one of those! I'm sure everybody else in the industry did something like that, but Atari had more money to waste than anybody else. So we started 5 of them, and by God, they were all big, big budget operations. They were really, for one of them, they set up an entire building as a studio for one game. I mean, they were really going to go do this on a big time basis because video disc games were the wave of the future. Everybody knew that, except for one rotten cynic standing up in the ivory towers of Atari Corporate Research saying, no, 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 video disc games are a fad. They'll burn out in a short while because they're theoretically wrong. And I was right. Everybody else was wrong. And I'm fairly proud of that because at the time I was universally ridiculed within Atari at least. Everybody said I was out of my head because it was, just look at the numbers, Crawford, look at the way this thing is selling. And they were right, the numbers were fabulous in the summer of '83. By the summer of '84, the numbers stank. And the reason why, any idiot can look, crunch per bit ratio stinks. Sure, you got a lot of data, but what do you do with it? Well, you just take it off the video disc and shoot it up on the screen. That's all. You don't crunch it at all. What does the player actually do? What kind of crunching do we have on his bits? Well, you, jump, and what were the commands? Forward, backward, I forget. But you had just a few buttons that basically said, you know, jump to the next sequence or continue on with this sequence. And so the amount of crunching that it did on data was almost none. It was basically just a little selector program, not much different from the, you know, a jukebox that selects the record. Oh, we'll play this record now. So very low crunch per bit ratio, extremely data intensive, no process intensity, result, not much gain, an abuse of computer technology, and it got absolutely what it deserved.
Yeah, but there were some that actually, in its defense, Fatty used to the game called Cobra Command.
Yeah,
Mach 3 wasn't bad. A guy named David Reardon did a game named Freedom Fighter. There were some good products that actually earned well and still earn well today. Maybe the biggest failure was that the hardware itself, the disc player, didn't function in commercial applications for more than 6 weeks at a time.
Okay. In fact, there were some things I noticed where they used the video disc not as the dominant element in the game, but it was just
the background.
backdrop. Yes.
Star Rider did that, except they took it, they made the image size twice the size of the screen so you could hand it back and forth as you're moving forward.
Yeah.
There were some good applications. Once again, the disc player itself didn't work.
Okay. But I would say this almost proves the point. That is, when you did another game that did have some process intensity, okay, you also had the laser disc in there as well, then it worked fine. But what the success arose from the process intensity. And if you don't have the process intensity, you lose. So I'm going to stick to the principle.
There was, speaking to that, Mach 3 did take data off of one of the audio tracks as data about what was going on the visual image. So where targets appeared on the video disc image, the computer knew that because it was processing a digital stream of data off of one of the audio tracks. So there was a reasonable amount of data that was being acted on, and then little target things were superimposed over those and kind of attempted to digitally juxtapose themselves over what are targets and stuff. So that was a little more interactive, had a little more intensity than just a thing as a dynamic background.
Yeah, I'm not trying to shoot down the technology by itself. Someday, video disc games will be worthwhile.
But some of the games are actually good.
Okay.
You can't just say because there were some that were bad, all were bad. There were some that were exceptional products.
Yeah, I'm not trying to say video disc is bad. What I'm saying is data intensity is bad. If you use a video disc in a process-intensive fashion, then yes, you can do something good. The problem is, it is very easy to be seduced by all that data. That is, when I walk in with a technology that has more data than you ever imagined in your life, it is very hard for any engineer or designer at all not to be overwhelmed by that and let that overwhelm his design. That's the danger. When somebody walks in and gives you a huge gift, make sure it doesn't ruin you. You still have to stick to the principles. The game has to be good. The process intensity has to be there. And we are going to have big problems effectively utilizing these huge data-intensive technologies that are coming in. Let me at this point bring out one of the biggest arguments against my grand crusade for process intensity, and that is that most of the technological development we're seeing in the late 80s and expect to see over the next decade is going to be in the area of data capabilities on machines. We're seeing the processors get, well, I'll give you a simple example. In the last 10 years, we've gone from a 6502 running at 1 megahertz to a 68020 running at 20 megahertz. We're talking about an increase in performance of what, a factor of 100 maybe? Let's just say a factor of 10 to the 2. 2 orders of magnitude improvement in processing power. At the same time, we're talking about typical home computer going from 10 years ago, 4K of to typical home computer, well, I don't want to say 512K because It's tricky. I used a 68020. Several megs of RAM at least. So we're talking about perhaps 10 to the 3 orders of magnitude increase in just RAM. Now let's talk online storage, floppy, hard disk. We've gone from cassettes that were effectively maybe 4 to 10K up to hard disks which go up in the megabyte range, 20, 30 megabytes. We're talking here, again, at least 3 orders of magnitude, maybe 3.5 orders of magnitude. In other words, the data capacities are growing faster than the processing capacities. In the next 10 years, we don't expect to see a big leap. I mean, if you compare a 68020 to a 6502, and we go 10 years into the future, do you really expect 10 years from now to be looking at something as much better than a 68020 than a 68020 is to a 6502? I don't think we're going to see that much, no.
It's going to be parallel processing and transputers and all that kind of
Not 10 years. That stuff is coming, but I think that's a ways down the road. In fact, I would be surprised if we're still screwing around with the 68OX and OXO and the 80OX or 80 whatever series through the end of the century.
Oh, really?
Software
lots of moving massive ranges of processes and data here and data there. I mean, I've seen tons of Japanese games with 68,000 microprocessors moving just reams of data and background and controls and blips and bloops and sound that a fun game it didn't make.
Oh yeah, okay, just moving it around. Sure.
But I mean, even in their perception of fun.
Okay.
You know, they had lots of input devices and lots of data and lots of...
I'm not saying that if you've got process intensity, you've got fun. I'm saying that if you don't have process intensity, you don't have fun. It's a negative rule, not a positive one. You cannot, in fact, I'm going further than that. I'm saying if you don't have process intensity, you don't even have utility. You don't have good software if you don't have process intensity. If you do have process intensity, you can still have bad software. But you don't even get out the gate without process intensity. This argument is compromised by the fact that data capacities are climbing so much faster. In the next 10 years, we do expect CDI to come in. And CDI is going, we are going to break out, have many, many megabytes of data available online, very fast access times. There's just a lot of reasons to expect data to play a larger role. However, my fear is that we will all be seduced by it, that we will just create rather stupid games that really don't do very much. If you want to get an idea of really the quintessential of this, look at a VCR game sometime. Get yourself one of those video cassette games. Have you heard of these? Get that and play that once. Cost you, buy one for incredible technology.
We have one.
Okay, good. And play that as an example for yourselves of why you don't want to do data-intensive stuff. Because there's a lot of data and no process. Well, very, very little processing in one of those. And that's why it's so ghastly boring.
I'll go along with you about interaction. I mean, what you're describing in bad games is lack of interaction. I mean, what really is the difference between a flight simulator where you have a database that's a relatively small data set that gets manipulated every single frame to produce a new view of the cockpit, which would be, in your definition, very high operations per data, with a huge bank of memory that has already pre-processed. I mean, you might want to count that, but frankly, that's all a moving picture image is. It's already pre-programmed all of that and has it in storage. Now, films and videotapes are limited that they can only put them out linearly. It's like, it would be like trying to access data off a tape drive, but you could random access the frame. What the hell is the difference? I mean, I think what you're talking about is interactivity.
That is one of the other objections. Basically, hey, process and data are the same. Any algorithm-driven thing you can substitute with a data-driven approach. You can table drive anything that you can formula drive, and that's true. But that's looking at it from too low a level. That is, that's a programming technique issue. I'm talking about grand issues of design. And the programming technique, well, no. That's a matter of how you implement. That's, how are we going to get this program running?
You brought it up.
Okay.
You brought up datum and operations. And, I'm just saying, what I just described is an inherent contradiction. I don't want to give you a hard time about this, but if you're going to use these damn definitions, you should work this out. Number one is, like, you used the flight simulator, said this was good. You did a lot of data per operation. There's no damn difference by your own definition in visually or in how the game plays between that and as if it were retrieving story.
You're looking at the wrong data. The data I cited was not the view data. The data I was looking at was the input stream. What I said was, you take the joystick input stream, very few bits coming in, and how many operations happen as a result of that or related to that. You tilt the wings a little, how it recalculates lift and velocities and so forth. So that answer may be disingenuous because you're on to something here. The basic concept that that you can mix data and process and interchange the two. My defense on that is that that is a programming technique that does not enter in at the global level of evaluating what the program is doing. It is more of an issue that you encounter at programming time rather than design time.
Well, I just think you're defending something that doesn't defend it. If you just want to say it's interaction, that's fine. If that's your criteria of how much interaction is going on between the person operating it and the computer, I agree with you entirely. That's fine. But I just don't see what you're talking about.
If I can just maybe rephrase what you're suggesting is you're talking about input data, whereas you're talking about output data.
Well, but he's talking about the seduction of data. You're talking about output data.
Right, but given...
Same difference. You're talking about video disk, that's stored data.
In fact, that may be a distinction that resolves a lot here. Because if you look at all the examples I gave, the crunch per bit ratio I used was applied to what the user inputs. Word processing, spreadsheets, DBMS, in every case I was looking at the input data. And in games, we have the extra consideration that we have data that we keep as part of the game. That complicates issues further. I hadn't thought about that, about those two forms of data separated.
But given you have unlimited data, and you can store every possible view of a flight simulator, I still think the more processing you could do upon that, the more interactive and the better the game would be.
That's fine.
Right?
That's fine. It's just that
the process ratio to that data is still the higher the process ratio, the better the game.
No, that's fine.
Well,
but I'm trying to clear up here is, make the distinction, because you're giving video disc games, for instance, a bad rap. Because, or the VCR game, using that as an example, where the real salient point there is not how much data a video disc holds or how much data a VCR cartridge holds, which is a phenomenal amount more than you can get on your average computer. Salient data is how often do you input something into the game. In a VCR game, it's like never.
Yes.
In early video disc games, almost never.
Yes.
It's
I
your
think
level of interaction with that data.
That's fine.
Right,
If you want to define that as being the data we're talking about, great, no sweat.
Okay. It's also, it depends on, it's a big difference in what data we're talking about.
Yeah.
An increase in resolution of a particular scene doesn't enhance as much as, the process-intensive data, in a sense. The data that actually controls the game as opposed to just enhancing visual
I would take
awareness
issue
not
with
quite-
the way you're trying to explain this, because I would say, if you had this infinite number of images pre-calculated as a flight simulator, and I did absolutely nothing except shovel them to the screen.
I can do it a lot better.
And I did no processes to it other than have an extremely high level of interaction with each individual frame. And I could, based on the input that's coming in, shovel them out in a totally interactive manner. I would say, I wouldn't care that I wouldn't felt that I'd been seduced by the Force because
that's the point. But now add another process that creates an enemy out there that's also manipulating those data. Right? Is that more interactive now? That extra processing adds more. put a
I
second
would ask
process
you
out
to,
there.
you know,
But when
exactly
we're talking
what
about
you
an
mean by
infinite number of
deeply
images,
interactive.
my infinite number of images include every view of the enemy on those things.
Right, but if there's another process that controls that enemy, as opposed to you zooming around him, looking at him, right? And he also controls what you see.
It still has nothing to do with output data, because now you're
the
just
point.
you're still on interaction.
Well, still, but it's more
You're still
processing.
just
I
having
think
an
interaction goes up with more
Well,
processing.
okay, but the point is, you said don't be seduced by
The dark
by
side data.
the data.
Yeah,
Okay,
dark
so-
side data.
But what's I guess the question is, at that point, if we have massive sums of data available to you, and that's going to allow you greater processing time per se, even though your ratio certainly changes. You may not get as many processes. Your ratio is certainly going to change. You get a smaller ratio, but or the gap will be greater. But why not take advantage? Why is that? Why is that a bad seduction?
Well, in fact, what I'm arguing, I suppose the argument I'm making, imagine how you're 18 years old, imagine how your parents would feel if you won the lottery. And they'd feel good for you, like, wow, you got all this money now, but hey, look, don't go out and spend it all on girls and cars, okay? Try to be responsible with it. And I suppose that's sort of like what I'm saying here. It is so easy when you are suddenly flooded with far more than you could ever have imagined how to use, to misuse it.
Well, I think that's what's happening with the Amiga market right now, basically, is you've got the ability to have a lot more data, you can do a lot more things, you can move more stuff around processing. But, you know, you've got this beautiful slideshow, but you're not doing enough processing to have fun with. But
Well, the problem with the argument that I just put up was, I suggested, and or somebody suggested, an infinite number of things.
right,
The minute you say it's finite, and you commit your resources to shoveling the large but finite amount of data instead of doing processing.
that's the
That's the
problem.
danger.
Yeah.
That's
The danger, is now that we deal with a finite universe, if you use a large amount of data, instead of calculating, let's say, for instance, for my processing, I need a sine table, really great one, to 24 bits of resolution. I could do a formula that generated that,
Yeah, or
and
you
would
can do it on a table.
and would bring the 68,000, take that much away. Or if I had a lot of data and I use that to speed up my ability to do more processing, that's a good use of
Yes.
large amount of data, in fact, which nothing is happening to that table except I am accessing it.
Right, with
Let-
one view you're looking at a piece of paper, it's a waste, but if you bigger picture you're not.
Let me present a counter-argument there. The problem here is you don't interact with data. You interact with a process. It is impossible to interact with a fact or an image or sound. You interact with something that happens, something that thinks, something that does, rather than something that merely is. Now, it is possible to table drive all processes. It's just that any interesting process is beyond the reach of table driving. For example, here's an algorithm, sine, and very simple process, and bingo, here's a data table for it. Okay, great, we were able to replace a process with data. But who wants to interact with sine wave? I mean, what do you say? 30 degrees, 0.5. 45 degrees, 0.707. That's not a very interesting interaction. Suppose you wanted to capture a process that was interaction. For example, balance of power. Let's take all of the processes in balance of power, treat it as one monster equation, and let's imagine a data table that captures every response situation in balance of power. We're talking about a table, what is the googles in size, okay? It is beyond our reach. There is no way we can table drive that interesting process. So, yeah, we can table drive the little pukey things, but as soon as you want to start table driving something really worthwhile, you just ran out of space on your video disc. So,
Chris, can I describe balance of power a little bit? Having been in the guts of it, trying to trying to debug a process-intensive thing. It is difficult. I mean, in balance of power, there were 62 countries, and each one of these he gave a lot of data. Okay, he does use data, and he gave each country attributes like aggressiveness and prestige and friendliness and craziness and wildness and all kinds of stuff. And these data values were then changed throughout the process of the game. If you selected a country and sent in troops, well, maybe your prestige went down and you got in trouble, and other countries thought you were bad, and a whole lots of data changed, and you had equations that to this day, I don't know how I came up with them, but he multiplied prestige times friendliness and gave craziness, and shifted by 2 and got, wild and craziness. And out of this,
it just went on and on.
Out of this came a plausible simulation of the game, which I know took him 18 months of hard, incredible work. And yes, this could all have been table-driven had he had enough information to make this enormous table. But that, even if he had that, and maybe it would have gone faster, and he wouldn't have had to wait, 30 seconds for between every move. But the thing is that when he describes what the high-level design is the high-level design were these equations, was the process of taking the data, manipulating it, and changing it, and it's different for every turn. I listened to a speech like this before studying balance of power, and now, after doing balance of power, I understand what he means. It's kind of hard to understand it without a concrete example like that. And that's, I think, his point, is that, yes, you can have table-driven, and maybe you're arriving at this table through processes that you have to do. And maybe for expediency and because you're limited by the processor speed, you need to have tables. But the tables in the process is what you're really designing.
Just pre-process. Processing happens at a different stage.
Did that make sense?
You can get it ahead of time. But given something, with 10 variables with 10 states each, how many combinations,
No, the thing is, when you go through the page after page after page in balance of power of equations, just equation after equation after equation, and you start saying each of these is done to 16 bits of resolution, and it has 3 or 4 arithmetic operators on it. And so each time you have an arithmetic operator, you add the number of bits together to get the size of the table. You realize this thing just explodes on you. There is no way you could ever do this on a table. So, yeah, balance of power is pretty process intensive. I mean, the giveaway is when it goes off and says now, it goes off to process the turn, and this is a 68,000 running at 8 megahertz, and it goes away for 1 minute. And it's not shuffling bits. The disk drive is quiet. It's just sitting there going crunch, 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 crunch. That's a lot of crunching going on. So
and that's not outputting data to the screen, and it's not anything you even see. You never see it. It just results in an attitude of the game back at you for when you do your next turn.
How is that crunching reflected in the 8-bit machines that you ported it to?
On the Apple II, it's a fake. The Apple II version has bugs in it.
Is that table driven, or is it?
No, the guy somehow squeezed it into 128K of RAM, and on the Apple II, we did a lot of hard cutting in the game. The Apple II version is a serious subset of the main game, and even then, the guy couldn't get the arithmetic going. Their initial plan was they would do it in 4th. And I said, no, this will fail if you do it in 4th. And then they said, well, we'll do it in assembly language for speed then. And I, no, the equations, you're bound to make mistakes in the equations. And they plunged ahead anyway. I really insisted that if they do it in assembly, they do it in a macro assembler that does formula translation. And they just plunged ahead anyway, and the end result was there are unsoluble bugs in that game. It miscalculates things. And they beat on that programmer for months and finally just gave up and said, ship it.
New features.
Yeah.
They're features. Yeah.
Special features.
Let me bring together now the 2 main threads of today. I'm now going to integrate 2 main points. First main point I made this morning. Interaction is the very essence of what happens again. You anticipated me here, Cam. The second main thread is that processing is the essence of what computers do. I'm going to bring those 2 points together and say processing and interaction go hand in hand. In fact, they are I can't say they are identical, but they are very intimately related. That is, you can't interact with fact, you can only interact with process. Process is what makes interaction possible. And in fact, processing, the interaction that you create through processing, is another way of expressing the utility of a computer. When I talk about the crunch per bit ratio, the examples I gave with the word processor, what were you doing with the document? You were interacting with the document, saying, well, now I'm going to change this document. And I look at it, and I see what it's like, and I say, no, this isn't what I want, I'm going to change it again. The spreadsheet, you look at the budget, you say, how is this budget? Maybe I want to change something. You look at the numbers, and you say, now I'm going to change something. Again, there's an interaction going on here. The importance is not this fundamental change in paradigm of the computer. The old paradigm of the computer as the mainframe, and you just pour data in, and then it goes crunch, 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 and out come 500-page financial reports. The computer is a batch processor. That paradigm is replaced here in this new paradigm as a computer. New paradigm of a computer as something you sit in front of and interact with. You see the numbers on your screen, and you say, well, what if we change the numbers this way? You see the document on your screen, and you say, well, what if we change the document this way? You see the database manager, and you say, well, what if we look at this subset of the data, or we select this group of data? And you sit in front of the game, and you interact with the game. These are some major threads here, some big ideas converging. Interaction and process as something fundamental to what we do with computers. And I will go so far as to say that the computer game is the most interactive, the most intensely interactive thing we do with a computer. I mean, a spreadsheet, you'll sit there and stare at it for a while and think, and then you'll change a number or two. A game you sit in front of, and there's a much faster, deeper, richer interaction going on. It is a more intense interaction. The process intensity in games, I believe, tends to be higher than the process intensity we get in other applications. I will therefore make the truly outrageous assertion that the computer game is the highest expression of computeriness. Now, what I mean by that is not that we should throw away word processors and spreadsheets and DBMSs and just play games on them, but rather that the computer game just happens to be the application that the computer seems best suited for. Maybe that may not be the one that is most useful for, but if you look at any tool, let's take a hammer, for example. You can use that tool for many different functions. You can crack walnuts with a hammer, you can hit people on the head with a hammer, break windows with a hammer, you can bang boards out of tight spots or bang things into tight spots with a hammer, or you can hammer nails with the hammer. Now, all of these things can be done. And if you're in a situation where there's your car is wedged with another car, and you need to get your car loose, then that hammer is damn useful for separating the two cars. But the application of a hammer in which it shines its brightest is when you take that hammer and there's a nice 15-penny nail there, and you lean back and you go wham, wham, and 2 strokes and bam, that nail is in that wood. That is what the hammer was best designed for. The weight, the layout, the mass distribution, everything about that hammer was designed for a full swing back, an impact on a small object, driving it into wood, everything about that. This is the optimum expression of hammeriness. You can do other things with it, but the hammer is shining its brightest, driving that nail into that 2x4. I make the same claim with a game on a computer. That is, when a computer plays a process-intensive game, deep, rich, intense interaction going on between player and computer, the computer is shining its brightest. It is doing at its very best, what it was best capable of doing. It may be able to do other things, and those other things may be more important to us, depending on the circumstances, and a hell of a lot more productive and a hell of a lot more valuable. But if we just talk about the technology by itself, devoid of human values, I argue that the computer game is the highest expression of computeriness. Does that mean anything? Probably not, because it is devoid of human values, and meaning is derived from human values, so we can't push this claim too hard. But I certainly use it to tell myself, you know, when somebody says, well, it's only a game, or when somebody says, well, you only write computer games, whereas I do DBMSs or whatever, it is a nice way to smile inside and say, this guy doesn't know the first thing about computers. So, let me now change the subject slightly and talk a little bit about, I'm going to get increasingly grand, noble, idealistic, and glorious on you here, by talking about games as a medium of artistic expression. This is one of these bullshit